Okay, good morning, everybody, once again. And today we will have two lectures on Rayleigh fading channels and evaluation of different parameters in such channels, such as data transmission rate, bit error rate, and what are options to improve these parameters. So today we are going to have not really my prepared presentations, but I thought since we are anyway learning in English, it's okay to use existing presentations. I will just try my best to explain uh, almost everything we can see in there. However, some parts we might a little bit, how to say it, force it faster or skip and see how it goes. Yes. So let us start with the first part of the lectures. I have already uploaded both of these presentations in the Ortus, so you can follow them too. And accordingly, we are beginning with the part one about more, how to say it, this first part is more dedicated to evaluation of bit error rate of capacity, and the second part will be more related to how we can basically improve the situation. So we already discussed these channels on our first introductory lecture, and we already mentioned that there is such thing as a fading, when because of different obstacles, of different objects around us, signals are reflecting and arriving via multipath propagation to some reception point, where amplitudes of our multiple signals can actually add up and either improve or well, let us say, for example, we have our mobile device receiving signal from our base station. Yes, we have direct path signal, and we might have different scattered and reflected signals from different objects. Well, for example, we have one house here reflecting signal and one house here. Well, not really like that, but more like this. Reflecting signal, and there can be many more of these reflected signals. So it turns out that because of this reflection process, time travel of the signal is longer. And since we are using some specific carrier waves with specific frequency, called carrier frequency, yes, reflected copies will always arrive a little bit later, and depending on the traveled distance, the phase shift accordingly that we have this delta time caused by extra traveling time compared to the direct path. Yes, we will have the signal arrived at different time moments. For example, here that was this way. Here it will be a little bit smaller. Yes, and accordingly, we have different how to say it, phase at this time moment. So for example, if we take this particular, for some reason green is always like this. If we take this particular time moment, you will see that all the signals have different phase, and depending on these phases, the total value, because at this point we will have them added up together, and the total value can be either large or small. Sometimes it is possible that this will a little bit benefit us. For example, if it turns out that the phase shift is exactly the same as one period, for example, like this, then what is going to happen is actually our signal will be stronger. Yes, because what here we have the 0, here we have also around 0. Let me be a little bit more precise here. Yes. And after adding these signals, if we have here amplitude, let us say U, and here we're going to have well, U1, and here we're going to have U2, which might be different because of losing some of the energy during the reflection process. So the total amplitude of the signal is going to be more than it was. It was U1, but now we are going to get U1 plus U2 because we were lucky and the phase was delayed just exactly to be, how to say, coherent, yes, to be in the same phase for both of these two signals. Needless to say that it can actually happen exactly opposite way. So below here, I'm going to draw the opposite case when we are going to have worse situation. So let us imagine that we are going to start here. Yes, and the delay is half of the period. So now we are going to receive our second signal like this. It's also, well, I'm not really smooth drawing here, but the idea is somewhere here to see how it goes. Yes, so here signal is negative, minus U amplitude. Here it is positive, plus U amplitude. So in total, if we use the same notations, here amplitude was U1 and here amplitude was U2, which are not exactly same. And usually this U2 is smaller than of the direct path because, as I said, we lose some energy during this reflection or diffraction process. So in fact, we are going to receive smaller value of the amplitude for this signal because of this reflection. And the thing is that this process for fading channels is random. We already discussed that this time delay is a random process. And because of that, the amplification of our channel is also random. Yes, so we can say that, for example, this is our normal level of the signal, which we should get usually. And then we can basically receive both stronger than we should, like this. Yes, sorry. Need to have a little bit straighter line here, which is U1 plus U2. And accordingly, we can also deviate in the level below of our normal, U1 minus U2. And the actual amplitude is going to change basically in a random way. Yes, for example, like this. And many other possible random implementations of this process. Yes, so these changes will be random because of this phase is going to be changed randomly, and also gain for each of the channels also changes randomly, if you remember our first introductory lecture. So this in total will generate random signal strength. Yes, we can basically conclude it like that. And as you know, during the transmission, well, basically, I don't really know, did you have in bachelor level this course? You probably should have some telecommunications theory course in bachelor, but what exactly we were discussing there, I don't really exactly know, but I assume that you were talking about the error probabilities, about the codes that can be used to improve the error probability, about the data transmission speed, rate, or capacity of the channel, that is maximum possible rate. So basically we can say that capacity of the channel is maximum of the data rate that can be achieved in this channel. So actual data rate is always below this capacity, yes? And well, that's why it's called capacity. And also in this lecture, as I said, diversity will be explained, how we can improve this data transmission rate. Actually, I believe we already discussed bit error rate for quadrature amplitude shift keying modulation type last practical exercise, and we drawn one of the important how to say performance evaluations for the transmission system called well, basically noise immunity plot. In our case, however, in our practical exercise, we were plotting symbol error rate rather than bit error rate. So it was expressed like symbol error rate. Here, we are talking more about specific bit error rate. But you need to remember that we actually used gray mapping for our constellation, and we tried to, well, basically, let me draw part of this constellation, yes. And we tried to assign the code words consisting of bits to each of the constellation points so that the difference between code words would be minimum. For example, here we have 4 zeros. Here we are going to have 0, 0, 0, 1. Here we can have, for example, 0, 1, 0, 0. And here we are going to have 0, 1, 0, 1. Yes, so any combination of two neighboring points is different only in one bit. So here, for example, it's in this bit. Here, for example, it's in this bit. And basically, I don't know, another some color, yellow, for example. Here we have this difference in this bit. And finally, here the difference is in the second bit, yes? So that was called gray mapping, and that was the reason why we used gray mapping, to avoid needless binary errors, yes? So if we have the errors in the symbol, yes, for example, we have transmitted this symbol, however, because of the error in the channel, we have received this symbol. Then it will translate into a single bit error, yes? And needless to say that errors over shorter distance happen much more often than errors over this distance. So here, if, for example, this error would occur, that would provide in total 2 bit error rates, yes? So it's not always like symbol error rate can be directly expressed as the bit error rate. This depends on the noise, this depends on the mapping, and other factors as well. So it's not that simple to recalculate this error. However, if we replace each symbol with its actual binary code for TX site and RX site, we can evaluate by simply counting mismatching bits. So it's possible to obtain in a simulation way. Yes, we can simply add some modifications to our program. Well, actually, let me open this code we were working on our last lecture and explain maybe in more specifics. We are not going to launch the program and do it because it might take more time than I want to, but in fact, so it was quadrature amplitude. Yes, it was this simulation, as you remember. And here we have generated this map, yes. And our transmitted data was basically generated as the random numbers, integer numbers from 1 to 4, yes. And the same was for imaginary part. So we can always generate it as the binary, not really generate, but translate it into a binary. So here we, for example, have random numbers 1, 2, 3, 4, which accordingly translates into 0, 0, 0, 1, 1, 0, and 1, 1, for example. And similarly, we do for the second part, yes? And accordingly, the entire CAM16 symbol is going to consist of 2 such parts, yes? Which actually, I was a little bit wrong here, actually should be in gray code, yes? So that would be more correct way. So we are going to basically assign them in gray mapping style. The same way goes for the second part. I'm going actually to mark them in different colors. Here, yes, so 0, 0, 0, 1, and 1, 0. And similarly for the imaginary part, yes, 0, 0, 0, 1, 1, 1, and 0, 1. And then we are going to combine this random process. So we generate for each real part random number a copy of random number for the imaginary part. So this will give us in total quadrature amplitude shift keying symbol consisting of two parts. One part is for real and one part for imaginary. For example, I don't know, one of the symbols, let us say this symbol is going to have the following coordinates, yes? So -1 is matching 2, and 2 is matching 0, 1. No, wait a minute. Yes, it's matching 0, 1. So that would be the real part, yes, 0, 1, which is in blue color. And the same way, for imaginary part, it is also 2 and also 0, 1, which is in green color. So the total code word assigned to this point is going to be this. Yes, and similarly, during the receiving part, which is it's inside this function, yes, in demodulation function, demodulated data here, is done the same way. We just look at the constellation map, yes, and read the signal, and also get some binary code. For example, let us say that something very terrible happened, and this demodulated symbol was received as 1, 1, 1, 1, which in total would produce us 2-bit error rates. And there was only one symbol error. So it's possible to recalculate just by making some modifications to this code. Well, how to say it? It might be easier to make this map also in gray code. So basically, similarly like this, we are going to specify a matrix with all the gray code combinations. Yes, well, let me actually start it here. So CAM16 gray, yes, is going to be something like, for example, like these, yes. I'm going to use string notations. So -3 matches 1, which is 0, 0. And +3 is accordingly, so let me write it here again. 1 is 0, 0, 2 is 0, 1, 3 is 1, 1, and 4 is 1, 0. Accordingly, this is -3, this is +3. Yes, so that would give us 0, 0, and 1, 0 for the first one. For the second one, this is going to be accordingly -1, which is 2, and it's 0, 1, and 1, 0. Then it's going to be 1, 1, and 1, 0, and so forth. Yes, then we start a new row, which basically repeats the first half, and the second part is slightly different each time. Yes, so +1i, here is going to be 1, 1. Here we are going to have 0, 1. And finally, here we are going to have this point 0, 0, 0, 0. Yes, and similarly, we replace everything then remaining. Then, after we have received symbol, we find the indexes in this matrix and read the code word. Similarly, we do for the transmitted signal. It's a little bit difficult at once to tell how it's done, but eventually we will work with this later in our next practical exercises. So this idea will be described in more details. So, okay, let us continue, because I was spending now a little bit more time on this first introduction slide just to remind some basic concepts we are going to use throughout today's lecture, such as bit error rate and symbol error rate and so forth. So The structure of the transmission system is looking something like this. So we have the source which generates our binary data. Yes. We have the coding device, which is needed to reduce number of the errors in the channel. We have modulator, which accordingly, for example, in our practical exercise was using quadrature amplitude modulation 16. Yes. Then we have this channel of which we are talking right now in the lectures of our course. Of course, the channel adds noise, as you have already done so in more than one practical exercise, and the modulator accordingly tries to detect the signal values from the noisy version. Yes, so what the modulator actually does, it tries to get rid of this noise. So basically, of course, sometimes errors can happen, and that's when channel decoding takes its part and tries to correct as many errors in the signal as possible. So there are multiple possible coding approaches. Yes, so we can use block codes such as Hamming code, we can use convolutional codes, we can use turbo codes, LDPC coding, and many other different things. As a matter of fact, we are going to discuss later on some convolutional codes and approach called trellis-coded modulation. Trellis-coded modulation. We'll talk a bit about this a bit later, but the idea is quite simple. We assign the code words to quadrature amplitude modulation signal. Well, actually, maybe let us try and find in Google TCM CAM16 constellation. Yes, it's here. So here you can see that we assign for quadrature amplitude shift keying 16 code words in another way. Yes, so here you can see that we assign specific points, specific code words. So in this particular case, we have this 1B difference for these 2 points, which are not exactly near each other. Yes, you can see that usually for the gray coding, we would want to assign this difference, for example, for these 2 points, yes, because the distance here is much smaller. However, here we are going to use the convolutional code in this constellation. So basically, this is already coded data, yes. So this becomes much more hard, and actually, let me see if we can see the full constellation. So this is for phase shift keying and for CAM16 constellation. We'll talk about this coding later on, yes, because this is the topic for a separate lecture. But maybe we can find TCM for CAM16. Well, it doesn't really look like this. But this assignment would be slightly different than for gray coding, yes? If we put all these points up together, you will notice that well, actually, I might later on during the break make this in the same plot, and then I will just show you. This is not really a topic for today. I'll just want to show you the difference between gray coding and the TCM. So that's some idea of the advanced coding, yes, which we will consider during this course as well, just to prevent the errors from happening, which for the Rayleigh channel we discussed today will happen much more often rather than for simple binary channel, for simple noisy channel, yes, we have discussed so far. So here, a small reminder is made on white Gaussian noise channel, which we were using so far in our 2 practical exercises. In first practical exercise, we just used noise, and in the second practical exercise, we used this noise in the concept of channel filters, and we have also noticed that because of using these filters, we actually somehow improve our symbol error rate, because we do not take all the bandwidth of the noise, simply due to the fact that we use filtering, and the filtering basically limits the bandwidth. Yes, so for example, we had these filters designed, square root cosine filters, yes, which accordingly limit the noise bandwidth, which in theory is infinite. Yes, so basically this is the energy of the noise distributed in all the frequency band from 0 up to infinity. However, our filter limits this part, and the energy of the noise therefore is limited only by this amount that got through the passband of our filter. Yes, so here we have some F symbol frequency. Yes, and you have been able to observe this effect in the results. That's when we concluded our practical exercise 2. So here we are talking about no fading case, and we have already modeled this channel. So the idea here was quite simple. We had this channel response, which was actually this filter, root raised cosine filter, yes, impulse response. We have our signal that we need to transmit, and we have also noise, yes. So in this case, in this slide, yes, we assume that the channel impulse response is just a constant. So basically that means we have here some h value, and all the other values are simply zeros. Yes. However, we were able to show that if we use specific type of the filter, it is possible to achieve that in the symbol reading time intervals we have zero values. What happens between is not really relevant for us, right? But at the reading time intervals we have these zero. So this is somewhat similar, yes? And the noise adds to our signal, making it hard to detect. So we have specified signal-to-noise ratio for the REGN function we used in our second practical exercise in decibels. Yes, so basically this is ratio of powers, of ratio of signal power related to noise power. Yes, which can also be expressed from the symbol energy. Yes, basically here we have power, and received signal power is denoted like this, and because naturally during the transmission the power of the signal decreases. Yes, so we basically can say that here we have this level P, and here we have this level P multiplied by h squared. Well, this was actually gamma parameter in our practical exercise, which was smaller than 1. Yes, and accordingly this means that the power is going to decrease. And this gamma parameter was depending on the distance as well. Yes. Then we have this noise power, yes, which can be calculated by accordingly specifying the bandwidth for which we calculate this noise. So noise bandwidth, or in these slides we use W notation for the bandwidth. And this was the level of the noise power. So basically noise power spectral density, yes, which already been discussed, that filter limits the part of energy, and calculating this N0 with W bandwidth will provide accordingly this figure shape. Yes, the area of this figure, that is the energy of the noise, or the power. I'm sorry, the power, not energy of the noise, because here we have hertz, yes, units. So that is 1 divided by second. And here for this N0, we are having, how to say, watts per second. So this is the energy of the noise in 1 hertz, or we can say basically divided by hertz, power over hertz, yes? So after we multiply, yes, we multiply this with hertz, we are going to get simply power in watts. So this is in watts, this is also in watts, yes? And how to say it better? We specify this in decibels, so actually it's not really equal here, but can be converted. Yes, it's more correct approach to say so, because we can say that SNR is actually 10 logarithms of gamma. Well, gamma here is used for a signal-to-noise ratio as the power-wise ratio in linear scale, not decibel, not logarithmical scale. Yes, so we have used this in decibels. However, often we want to recalculate decibels into times, into well, basically ratio rather than decibels. Yes, and this is done simply by reversing this logarithm. So what we are going to do first is divide SNR by 10 and then calculate this as power. So for example, minus 10 decibel, according to this expression, would translate into 0.1. So that means that the power of the signal is 10 times lower than the power of the noise. Yes. We'll use this today a little also, so that's why I wanted to remind you this factor. Also, we can calculate signal-to-noise ratio via the energy of the signal, of the symbol, and spectral power density of the noise. If we consider that the basically power here, wait a minute, is it it's divided, not multiplied. Power is energy divided with time interval, and same way for the noise ratio. So here we also have it divided. This gives us a chance to factor out this basically symbol duration of our one pulse, yes, symbol duration. And accordingly, we are left with this expression, the energy of the symbol divided by the energy of the noise in 1 hertz. So this is another way to calculate this signal-to-noise ratio, which happens to be also gamma, yes, not really SNR. SNR usually we describe in our course. Yes, I'm just saying that in our course we are doing it like this in decibels. However, in this particular course, I don't know, was it like always in decibels or not? I'm just pointing to the difference in our course. So also we use Nyquist filters. Yes, we have discussed in last 2 lectures with the roll-off factor of beta equal to 1. So that means that we didn't have much excess bandwidth, yes, and this was delta F minimum required according to the Nyquist theorem. For beta equal to 0, we had this filter response, frequency response, yes, twice as large, yes. So basically that would give us double T symbol for beta 0. And for beta equal to 1, we have least yes. So basically, this is to make it simpler. However, as I said, it's always better to have a little bit extra bandwidth, not to use exactly beta equal to 1, maybe beta equal to 0.9, as we discussed in our practical exercises. So if we use, for example, quadrature amplitude, shift keying, CAM16, then we are actually more interested in calculating bit energy rather than symbol energy. Well, since each of our symbols for CAM16, for example, symbol 1, consists of 4 binary symbols, yes, for example, this type, then we simply calculate we divide the total energy of the symbol by the number of the bits per this symbol. So basically, bit energy is going to be symbol energy divided by the number of bits per symbol. So for CAM16, M is equal to 16, and that accordingly is for binary logarithm. Yes, be more specific, by log 2. And that accordingly is 4. Yes, so we divide energy of the symbol by 4 and calculate this bit energy. So noise is generated so that this power spectral density is actually variance of the normal distributed process. Yes, so this is a random process with a 0 mean value and variance sigma square equal to the desired noise power density. So that's what's happening inside this AVGN function. It generates Gaussian normal process, norm RND in Matlab, yes, where you specify, I'm sorry, where you also specify dimensions, yes, so basically number of rows, number of columns, and this defaults to generating random normal process with these parameters, mu equal to 0 and sigma squared equal to 1. That's how this function basically generates random process. However, if we'd like to have different variance, we can simply multiply square root of this value, which is actually this n0, which in turn is calculated. So basically n0 is calculated from gamma. Wait a minute. Let's write here. Gamma is actually energy of beat divided by n0. So that means that n0 is energy of beat divided by gamma, where gamma is specified in SNR. Yes, for example, we say SNR is 10 decibels, so that means gamma is also 10. And energy of beat can be calculated for our signal, yes, because we can calculate for each symbol of our CAM16 modulation its energy. And then we just calculate average energy of all 16 symbols. Yes, so basically we calculate for this symbol energy, for this symbol energy, for this, and all the other. Then we calculate average energy of the symbol, and we divide it by 4 to get energy of beat. Then we know what noise power density we need for this signal to noise ratio, and accordingly we know the variance as well, which is sigma squared, which we then multiply to this normal distributed signal. And that's basically how this function works. We could have actually written our own AVGN function. It's not really that hard. However, here we need to remember that for complex part, we need to distribute this noise power density into real axis and this imaginary axis. So each axis will actually have the half of the power density. Yes. So imaginary axis and real axis have only the half of the total noise, so that both axes will have n0 complex noise. Yes. So that's one thing to consider. Let us go further. Yes. So for the normal channels, which we have discussed so far, this impulse response is known. Yes. So basically this is path loss and also doesn't change. Yes. So if we say that we don't have much loss in our channel, for example, we don't transmit over long distance or we have very good cable, then we can even assume that this is actually 1 and we don't have much loss. Yes. And the signal to noise ratio, therefore, is a constant. However, for fading channels, this changes in time. Yes, this is actually a random process for fading channel, and therefore signal to noise is also going to be a random process. So here we have reminding how to calculate channel capacity. Yes, for the channel with noise according to Shannon's formula, yes, where W is the bandwidth of our signal, which is limited by our filter we are using, yes, and S and R is the ratio of signal to noise in times, not decibels, yes, so it is not in decibels, it's in converted relative units, yes. And by using this formula, we can calculate actually the capacity of the channel, the maximum data transmission rate limited by noise. Yes, because usually, if we don't have noise, we can say that basically our channel capacity can be almost exactly the same as bandwidth we are using. But however, because of the signal to noise ratio, yes, we are going to have smaller value. So here is logarithm of the base 2, yes. So let us assume that signal to noise ratio is actually 1, yes. Then we can calculate this logarithm and get this result. However, often, as you imagine, SNR is smaller than 1. That means that the signal is weaker than noise. And for that reason, we are not going to get here in these brackets 2, and the logarithm is not going to, logarithm result is not going to be 1. It's going to be smaller than 1. And accordingly, the capacity will be smaller than bandwidth, yes? So that's what's happening because of this signal to noise ratio. And furthermore, since the signal to noise ratio will change, the capacity is going to also not to be so, how to say, so constant value. So the maximum data transmission rate will also change in time. So if we express it in the beats per hertz, yes, so then we lose this bandwidth from this expression, yes. So we basically say that we normalize with the bandwidth, which is called usually the efficiency, spectral efficiency of the modulation type, for example, yes, which accordingly shows the Shannon's limit, how much information can be sent in such channel with this specified signal to noise ratio, and accordingly, as you imagine, we never really reach this limit in practice. So Shannon's limit is usually represented in form of such plots. Yes, so basically this is spectral efficiency or capacity divided by bandwidth. Yes, so efficiency is capacity divided by bandwidth. Yes, and it's usually like this. So as it goes for the quadrature amplitude modulation 16 signals, the theoretical maximum number of bits sent by one symbol is 4. Yes, so we might send these 4 bits of information without errors, yes, for quadrature amplitude modulation 16, starting from roughly 16 decibels of signal to noise ratio. Before that, as you can see, actually, we cannot send 4 bits. Well, if we look closer, we can see that we almost send 4 bits. However, well, if we don't have sufficient signal to noise ratio, even theoretically, we cannot hope that all these 4 bits assigned to one symbol will go without errors. Yes, errors will happen, and the lower signal to noise ratio is, the more errors can happen to our 4 bits. Yes, so this is also specified for specific error probability. Yes, so error probability of 10 at the degree minus 6 is observed for specific signal to noise ratio, as you know from noise immunity curves, which we have plotted in the last practical exercise. Yes, so here we have this SNR, here we have this per error. And in addition to that, we also have this bandwidth as a factor. Yes, so basically, if, for example, I'm going to increase SNR here, the error probability is also going to reduce from this plot. Yes, and here, for example, we are going to have error probability I don't know, maybe 10 to the degree minus 7, yes? And this line, this uninterrupted line, black colored line, is actually Shannon limit. Shannon limit. And as you can see, the only way to approach to this Shannon limit here, for example, is to use more symbols for quadrature amplitude modulation. So somewhere here, we are going to have, let us say, that would be 256 CAM, yes, and so forth. Here we are going to have 1024 CAM, and so forth, so forth, so forth. Yes, so that's the only way. However, as you know, increasing the number of signals also reduces the distance between these signals, and this makes it much harder to detect these symbols. Yes, so we need a very, very strong coding, and currently only for some specific points we might get very close to this theoretical Shannon limit. This basically dotted line shows how close we have actually gotten. We didn't reach this theoretical limit just yet, unfortunately, yes, and there is a lot of working to be done, including, as it's mentioned here, adaptive demodulation and coding. So the codes that adapt to changes of the channel, since the Rayleigh channel actually changes in time. So let us now go to the fading channels. Yes. What happens for fading channel? We can consider fading channel to be multiple channels in one package. Yes. So basically our fading channel, actually its model consists of, for example, in this case, from two additive white noise Gaussian channels with different capacities. Yes. And we have some kind of random switch that basically randomly connects our signal transmission to one of the channel inputs, and then we read the output of these channels. So what happens here, that we, with equal probabilities, so that would be P1 50%, 0.5, and P2 also 0.5, transmit data through either one of these two channels. Yes. Then we can write that the capacity of such channel is going to be accordingly average of the capacities for each of the channels. So for the first channel, we had capacity of 1 bits per second per hertz. And for the second channel, we have 2 bits per second per hertz. Yes. Now, if we calculate the average, mathematical average, yes, expectation, then we would put here capacity 1, here we have capacity 2, multiply, add up, and have 1.5 bits per second per hertz. Yes. Now, if the switch is fixed at the position 1 here, then we will have all the time capacity 1 bit per second, which is actually even lower. Yes. Well, this might be some very bad channel, and this is something better channel, yes, than let us say than the first one, yes. So only part of the data goes through the first channel, and the second part goes through the second channel, yes. And the thing is that we can put much more signals, and that's basically what Rayleigh fading channel model is, much more of these channels. Yes, so we can say that here we have many different, let us say, M channels. Yes, and each has its own signal to noise ratio. Yes, which accordingly gamma 1, gamma 2, gamma 3, and so forth is a random variable. So this is random. So that's what's happening for Rayleigh channel. This signal to noise ratio randomly changes, and we can say that our switch connects with certain probabilities. There is a certain probability for this to happen, certain probability to happen for this, certain probability for this, and so forth. And in fact, we already discussed what is the probability distribution. It is called Rayleigh distribution, yes, that, and hence, accordingly, the name for the channel, Rayleigh channel, yes, because these distributions are in accordance with Rayleigh probability density function. Yes, and then if we calculate this capacity in accordance to this distribution, then we are going to get C as probability of the first channel multiplied with the first channel capacity plus probability of the second channel multiplied with probability of the capacity of the second channel plus probability of the third channel. Yes, these probabilities are not really equal. They are different, yes, because if this probability would have been equal, then we would just divide by the number of such probabilities, like in previous case, yes, where we had only two channels with same probabilities, and hence each channel only had 1 divided by 2 probability, and that was it. Here we have different probabilities, and so forth up to our last one, yes, PM multiplied by capacity of the mth channel. So now, if we say that the difference between these gamma is delta gamma approaching to 0, very small. So that in that case, this will be infinitely large amount of the channels, and this sum will convert into the integral. Yes, and that's what's happening exactly here. Yes. So here we have this integral. This is actually the capacity expression. So capacity divided by bandwidth. We usually divide by this bandwidth due to the fact that we don't want to be tied to some specific bandwidth. So as you know, we use some filters, yes, which we have been calculated. For example, the same root raised cosine filters we have simulated last time, and all these filters have specific bandwidth. That means that the system that uses this filter will also have specific bandwidth. For example, in LTE we can have different bandwidths, like 1 megahertz, 2 megahertz, 5 megahertz. Yes, we can have even 10 megahertz. For Wi-Fi, we have wider bandwidth, for example, 8 megahertz, 40 megahertz. Yes, and does it really depend? Does the efficiency of the channel really depend on what megahertz bandwidth we use? Not so. It depends on the properties of the channel, on this randomness, on this Rayleigh distribution, and much more. So in order to compare, for example, this LTE system with this Wi-Fi system, it's beneficial to normalize our capacity with the bandwidth. So in that case, they will be in the equal conditions and can be directly compared, because it's quite hard to compare the Wi-Fi capable of reaching, for example, 600 megabits per second and LTE reaching, for example, for 10 megahertz. For example, I'm not actually claiming that it is true. I'm just considering that, for example, it's going to be 100 megabits per second. Yes, it's quite difficult to compare this performance because the bandwidth is different. However, once we divide with this bandwidth and get, for example, here 10 megabits per second per hertz, and here we are going to get accordingly, if we use 40 megahertz bandwidth here, we are going to get 15 megabits per second per hertz. Yes, then it would be much clearer that this is more efficient. Yes. So for that reason, we usually factor out this bandwidth, yes, and assume that if we need to consider bandwidth as well, we are going to simply multiply it, yes, for the specific system. And this is actually the probability distribution function of the Rayleigh function, of the Rayleigh, yes, distribution. So it looks like somehow like this, yes. Here we have this gamma parameter, and here we have this probability of, well, basically gamma I and probability of gamma I, yes, which is not really, well, maybe not exactly like this. Rather, it should look. Rayleigh distribution also can have different parameters, yes. But the thing about Rayleigh distribution in comparison to normal distribution, let me also draw normal distribution here, is that normal distribution doesn't have this long tail. Yes, you can see here that this is a long tail. Also, Rayleigh distribution is always positive. Yes, so here we have 0 and the value is always greater than 0. And we have a quite small probability, however, this is existing, that the signal-to-noise ratio will be too large. Yes, so basically it is possible, yes, to have very, very high value of this signal-to-noise ratio, but under a very, very small probability. And the number of such cases with different values is infinitely large. So yes, as I said, this basically is the integral form of that equation when I calculate the total capacity as C1 multiplied by probability 1 plus and so forth. Yes, which accordingly for limited number of events would be Ci, which can be calculated accordingly by this formula, log 2 1 plus gamma I, and probability Pi, yes, which accordingly is function of gamma I. Yes, so basically this equation specifies capacity. Yes, and probability density function for Rayleigh process can be easily found. Yes, it's like this. So we might even Google it up, Rayleigh. Well, actually, we are going to have this formula later in the second part, so let's not waste right now time, because I can see that I already am a little bit long. Yes, and this accordingly integral, if we factor in this function here, can be changed, yes, and the result can be expressed basically like this, yes, where this E1 is this, how to say it, Laplace function integral, which, as you know, cannot be really calculated analytically, yes, but it can be calculated numerically, for example, by using Matlab functions such as exp integral, yes, in Matlab. And accordingly, we can use these functions in Matlab to calculate this capacity. So basically, it's hard to calculate, yes? Well, basically because this integral cannot be really analytically calculated, only approximately by using numerical methods, yes? However, we can use some, how to say it, simplifications, yes? Some assumptions to get approximate value, yes? And in that case, we can say that to get the approximate value of the capacity, we need to know the average value of the signal-to-noise ratio, mathematical expectation, yes, coming from that distribution of Rayleigh. So that's how to make it simpler, yes. Considering that we calculate this mathematical expectation for Rayleigh process, yes, it is roughly, well, at least we can say that not exceeding, yes, but we can say that it is roughly the same as calculating the capacity for the average SNR, yes, so capacity calculated for gamma average, yes, mathematical expectation. So that's how it's approximately calculating, yes, and if we do so for the signal-to-noise ratio, average signal-to-noise ratio, yes, we can see that the capacity degrades, yes, the more, how to say it, the higher the signal-to-noise ratio, the higher this difference, yes. Here we almost have no difference at all, but as we will go further, this difference is going to increase more and more, yes, related to the AVGN channel. Now, however, this greatly depends on how fast this switch connects. Yes, as I said, the probability of connecting this switch to any of these positions is not equal. And for some channels, the probability is higher, and for some channels, the probability is lower. So yes, again, if we draw the probability density function for Rayleigh process, you can clearly see that the maximum is somewhere here. So this is maximum probability, which represents one of these channels. And other channels are accordingly in other positions, yes? There are even a lot of channels which have very small probability. However, the probability is present, yes? It's not zero. So there is a probability that our channel can be blocked, yes? So assume that for some specific channels, we have so small SNR, for example, below 0, yes, meaning that the noise is stronger than signal, or that is the same as gamma is below 1, gamma I, yes. And in that case, there is a probability of, how to say it, not transmitting data, but losing data, that there we have outage of the signal. We don't have received signal. And we can actually calculate this probability, yes, if the data transmission rate is below some specific threshold, as the probability of this happening, yes. So, as I said earlier, capacity shows the maximum possible data transmission rate, which is not really guaranteed in the channel. Yes, the thing is that we can actually have errors even more than we should statistically in average, yes, and therefore we can not receive, for example, specific block of information. So, yes, as we said, therefore, there is the probability of the outage. Yes, the probability of the error. And it also depends on the distribution of our channel. Yes. So, which is Rayleigh distribution. And again, here we have some mathematics how to calculate this probability. Yes, so we specify the minimum signal-to-noise ratio which suits us. So basically to avoid this outage, yes. And basically that means this integral basically means the following picture. Yes, if I try to explain it graphically, so that we have this function of the Rayleigh distribution. Here we have gamma, here we have function of gamma. Then we specify some minimum gamma that we want to have. Yes, and therefore we calculate this area as an integral of this function from 0 to this limit. Yes, and accordingly that will be probability of the outage, because we are going to start receiving data only if gamma is more than this gamma minimum. Unless we have this true, we will have outage. Yes, so this is probability of the outage. And this is accordingly probability of the transmission, or how it else to say, 1 minus P outage, yes, of the opposite case. So in order to start transmitting data, we need to have specific minimum signal-to-noise ratio, and the probability for this outage therefore can be calculated by simply substituting this limit here, yes, as of this integral. Again, this is quite difficult to calculate analytically, but it can be approximately expressed as this value, yes, where we also need to know average, how to say it, mathematical expectation of this random Rayleigh process, which can actually be calculated, yes, according to some specific formula. So outage probability for this average signal-to-noise ratio, which is, wait a minute, 10 decibel. 10 decibel, okay. And as you can see, the probability of the outage as it, how to say it, decreases, then the capacity of the outage also decreases. So this is not really capacity of information. This is the capacity of, how to say it, opposite of the information, that we will not send information. So we are interested to have this as 0. So that means that all the other part, yes. So basically, we can plot the second plot, which is accordingly looking somehow like this. And that would be the capacity of information, yes? And it's clear, if we have this high, then we are left with 0 for our information capacity. If we have it here, for example, then the capacity will be the missing part to this 1, yes? And so forth. So the capacity plus C out is going to be 1, yes? And accordingly, if we have the C out high, there is nothing left for our data capacity. So this is a model, mathematical model, yes? We say that there is some abstract capacity of the errors, yes, which occupies our useful capacity of data transmission. So we say it like this. And for the, how to say it, channel, we can assume that for wide Gaussian noise channel, we don't have this channel impulse response changing at all. Yes, so we have this H1 for each of the blocks sent to from transmitter to receiver. Yes, for if we have fast fading, yes, meaning that during our transmission the properties of the channel change very fast, yes, then we can calculate this capacity as the average of the capacities for each of these transmissions, yes. Now, if we have fading, slow fading, let us say so, yes, then the channel properties change much slower. For example, we have sent some block of information, then for the next block of information, channel properties change and so forth. And we can calculate accordingly our capacity as 1 minus C outage, yes, which can be accordingly calculated from the Rayleigh distribution function according to this integral, yes. Well, this is actually only the probability, yes, of this outage. And it can be accordingly expressed, yes, as a probability. Okay, so if we go further for the bit error rate, how does it change for the Rayleigh channel? Then we don't have these formulas we had. So normally for white noise channels, for example, binary frequency shift keying, we actually have some formula which we can use to evaluate the error probability, yes? So this was depending on the distance between signals. For example, if we talk about binary phase shift keying, then we have real signal, for example, +1, and real signal -1. And the phase difference is P. And there is some distance between signals, which can be calculated as the maximum signal minus minimum. So +1 minus -1. And that's the factor of 2 coming into this expression. This function Q is also an integral, yes? Also integral that cannot be really calculated. it's the same form of the integral a power of minus t divided, integrated by t, yes, which in analytical expression cannot be really solved, but it can be solved numerically, yes. However, here we have it divided by 2, there we had it in previous form, yes. If we compare this integral, then we have it x squared divided, I'm sorry, 2, yes, I missed here square, because without the square, this is quite simple integral, yes. However, now if we have this squared, it cannot be really solved. My mistake, sorry. Yes. So for this, we have x squared divided by 2. Also, we have this factor, which can be actually put outside of the integral. It doesn't really matter. But the difference here is that we have here calculated a power of minus x divided by 2 by x, yes. Previously, this was almost, and yes, and the limits are from x to infinity. I just want to show you that this is actually almost exactly the same integral, yes, as it was here. Yes. No, wait a minute, it's slightly different. So here we have like this, yes, which is also not really solvable. So for that reason, we used this function for this integral. And for that integral, we can use, well, it's not really mentioned here, but I'm sure we have R function in Matlab, which can be used to calculate, well, basically it's going to be 1 minus q, yes? So 1 minus q is calculated by R. So, no, wait a minute. It's not like 1 minus q, it's more like 1/2 minus 1/2 q. And then accordingly, we can express this q from this R as no, wait a minute, something is wrong here. I do remember that expressing the q actually gives us this result. Minus here. And x divided by square root of 2. And here we have x, like this. So this is actually how we can use Matlab R function to calculate this q. Yes, so basically this is our x, square root of 2 SNR, then we divide it by square root of 2, and then we calculate our q. Similarly, for QPSK, we have another formula that we can use to calculate this error probability. And this is possible to be calculated. For example, if you use grade coding. Yes. It depends on the mapping, yes, of course. And well, basically, we can say, since we use gray coding and symbols, neighboring symbols are roughly more or less secure, yes, for gray mapping. And for gray mapping, here we have 1, 0. Because the most probable change, the most probable error will be over shorter distance, not over this distance that is longer, yes. Also, there are only 2 cases for this longer distance, whereas there are 4 cases for these shorter distances. So all in all, we assume that all the errors are happening in symbols are basically leading to only 1 bit error. Yes, and accordingly, since our symbol consists of 2 bits, we need to take half of this. Again, this is not really, how to say it, theoretically correct or mathematically exact. Yes, this is a rough estimation, which often in simulations comes to be true. For multiple pulse amplitude modulation constellations, there are another formula. So I'm not really going to spend more time here, yes, but I can say just, for example, for quadrature amplitude modulation, we put here 16 for M to get CAM16, and we can actually calculate error symbol error probability, yes. It's not that easy to calculate bit error probability. It's not really like a symbol divided by 16, because there are much more different possible distances here. It's all in all much more difficult to calculate. And accordingly, even most probably impossible to calculate by formula. We have to resort to some simulations, because also mapping matters. Do we use gray mapping? Do we use natural mapping? Do we use trellis coded modulation mapping? Yes, and well, it depends greatly. So for Rayleigh fading channel, the level of the amplification for channel isn't really constant. Yes, so for Rayleigh channel, you can clearly see that this level H for the channel, yes, clearly changes over time, and it changes quite fast. So that's the problem of these Rayleigh fading channels, and as you imagine, this will lead to much more errors. So if we would simulate such channel, and next time we are going to have practical exercise that will exactly do the same thing to perform this simulation of the Rayleigh channels, yes, we can evaluate the error probability by using these formulas, yes? And we will see as a result that the error probability is much, much higher, yes? For example, if we use signal-to-noise ratio of 10 decibel, then for our previous channel models, the error probability would be somewhere roughly, somewhere around 10 of minus 5. That means that we only have one error in 100,000 bits. So you transmit 100,000 bits, and roughly on average, yes, you will get only one error in these bits, which is more than easy to correct. Yes, you only need some Hamming code, correcting one error in a specific block, and you will be fine. Now, if we have Rayleigh channel, which is usually what's happening for any moving objects, yes, the error probability is now going to be around 10 of minus 1, which is one error in 10 symbols. So roughly, we have like 10,000 times greater error probability. So yes, as you can see, it's quite difficult to get this error probability for Rayleigh channel. Yes, so we need to actually have much higher SNR, which has been calculated. Yes. Sorry, it was calculated for error probability of -3. So here, okay, let's take this example of -3. So -3 is somewhere here. Yes, and accordingly, eventually, for some signal-to-noise ratio, we are going to reach this level as well, but it's going to take us 17 more decibel to get this error probability, which is not that good, actually. Yes, this is considered quite bad channel for this error probability. Good channels should provide -5, -6. These are some channels we can really work with. These are acceptable error probabilities. Yes, so here we have 17 decibel difference just because of the fact that this channel has Rayleigh fading, which comes from different objects, yes, which, as you imagine, is natural for city. And furthermore, considering that you are having mobile phone and are moving in the city, these channel properties also change in time. So even though we have perfect knowledge about channel in both cases, Rayleigh channel shows much worse performance. Yes. So The reason for that is that there is quite large probability of deep fade. Yes, so basically for Rayleigh channel, for example, if we specify some gamma minimum here, this probability is very large compared to the probability of successful reception, which is here, yes. And that is the main reason for these errors, because up to this place, we are going to have some short outage, yes, which accordingly prevents us from receiving our data. Here again is the same formula, yes, so Z is, well, basically 1 divided by gamma, yes, 1 divided by gamma. This is our gamma average furthermore, yes, if I recall correctly. And this is the probability of being in this deep fade, yes, 1 divided by gamma here. So not really gamma, but 1 divided by gamma. Well, basically opposite, yes. If we usually say that this is signal to noise ratio, that would be gamma. Then 1 divided by gamma is actually, well, you can say that noise to signal ratio. Yes, opposite ratio. So this is the probability, and basically if we make some simplifications, assumptions, we can conclude that this is actually roughly linear, yes, probability. How to say it? Not really linear, maybe hyperbolic, yes. But here we have -1 degree. It's inverse, yes. We can say that it's inverse to signal-to-noise ratio. The higher signal-to-noise ratio, the lower probability will be, yes. So that's quite clear even intuitively, yes. If you have, for example, SNR high, then the probability is going to be low. And vice versa. For the lower SNR, we are going to have higher probability of the outage. So if we talk about some diversity, how we can improve the situation, then we can actually change the slope of this line. Yes, for example, to be like this, or like this, or like this. And in that case, here we are going to have 1 divided by gamma. Here we are going to have 1 divided by gamma square. Here we're going to have 1 divided by gamma third degree, 1 divided by gamma fifth degree, and so forth. Yes, so that will improve the performance. How do we do that? Well, the thing is we can use multiple antennas. Yes, so you already most probably are at least familiar with the concept of MIMO antennas. Yes. However, I should add that there exist different other types, such as single input, single output, seesaw antennas, yes, single input, multiple output, and multiple input, single output. And of course, multiple input, multiple output. So in total, there are 4 cases of this antenna. So here you can see single input. So we have signal transmitted, and this signal has arrived to our location via multiple paths. Each of the paths is having its own channel properties, yes. And basically what we have here is superposition of all these channel signals, yes. So that's what's happening for Rayleigh channel. And because of that, here we are going to have this 1 divided by SNR or gamma, as it was mentioned earlier here, this. However, this will only work if we do everything here correctly. Yes, we need to receive this signal correctly. So here we can see that we perform this reception of the signal. And we also assume that this signal we have received is not correlated to any of other channel signals, yes, which is not true for simple approach. Yes, so that means that we actually need to have multiple antennas. Yes. So we have one transmitted antenna, and we have one antenna here, one antenna here, one antenna here, multiple antennas. Yes. So using multiple antennas, we can actually improve this diversity exactly by the number of the antennas. So we have n antennas, and we are going to get much better slope of that line than this plot. Yes. And how is that working? Well, it's quite difficult, and we'll talk about it a little bit later, but the idea is basically to use some weight parameters, yes, and which should compensate channel. Yes, so basically similar to equalizing ideas. Yes, this can be again written in matrix form, but it's not really important right now for us to get this, because we'll talk about equalizers later. Yes, and the idea is that we need to find these coefficients. We don't know them, and it turns out that they are somewhat, how to say it, inverse to the channel properties, and this comes naturally. So in order to compensate the effect of the channel with some response h, we need to have the inverse number, so that double W with h would produce as something like 1. So the total effect would cancel out. Yes, so we need these weights to cancel out the effect of each channel. If we can find them, then everything will be fine. And that is the idea of equalization. Yes, and basically here is some more mathematical background, which I'm not going to delve into now. Yes. And here you can see that changing this n indeed will improve the situation. So for n equal to 1, we had linear function somehow like this. Yes. So this is the idea of the Rayleigh channel and how it affects error probability, how it affects channel capacity. So on the next lecture, after a short break, we are going to discuss some more of how we can basically fight this effect. Yes, how we can improve this probabilities. And also, I will add a little bit more on the background of the Rayleigh fading, on the error probabilities, on the Doppler effect, which also comes in place. Yes, and basically we'll continue after a short break. So let us maybe make a little bit longer break, as we had quite a lot of information right now, and we need some break. So I think it will be fine to continue at 10 exactly. Yes, with the second presentation, which maybe will not be so mathematically intense. Yes, I think it was not so mathematically intense, which will be easier. And then after the second presentation, if I manage to get Matlab working, I will show you some example of simulation for Rayleigh channel. So are there any questions so far?
No, sir.
Okay, so then let us have a break, and at 10 we continue. Thank you, and see you in 10 o'clock.